In this video, we are going to do 7 most popular matrix questions. Now, matrix are one of the most important data structures because of two reasons. Number one, they have huge real life application. Number two, they can very easily intermingle with other data structures that are already so prevalent in the computer science fundamentals. Data structures such as graphs and arrays, programming concepts such as sorting and dynamic programming, they are all very closely related with matrix. So that's why in this video, I have taken the 7 most popular matrix questions, put them together, and they cover everything related to matrix. I hope you find this video useful, and let's get started. And my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do a very interesting LeetCode problem called Game of Life. Now, if we see some of the popular companies who have already asked this question, there are companies like Amazon, Bloomberg, Google, DoorDash, Microsoft, Snapchat, and Facebook. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and also very well-liked problem on LeetCode. Basically, we need to find the next state in the game of life. Now, the question is, what is game of life? Originally, this has been created by a mathematician named John Horton, where we are given a board that is made of m cross n grid. So there can be like any 2D grid of m cross n cells. Now, the thing is, we are given the initial state of a cell, and the possibility is that any particular cell can be a live cell, so that is represented by value number 1, or it could be a dead cell that is represented by value number 0. Now the thing is, we are given the original cell in some formation, and then we need to find the next state of the cell using the rules that are provided by the game of life. So over here I am basically creating a table from these 4 given rules, and then we are going to use this table to see that what would be the next state in game of life and how would we be able to solve this problem. Okay, first one is, it's saying that any live cell with fewer than 2 live neighbors dies in the next state due to the underpopulation. Okay, so if the current state is live, so we just note this with value number 1. Okay, so if the current state is live and if the number of neighbors is less than 2, okay, so the number of neighbors is less than 2, then the next state is going to be 0, or the next state is going to be dead state. Now the next one is that if any live cell with 2 or 3 living neighbors will live on to the next generation. Okay, so if the current state is 1, if the number of neighbors is either 2 or 3, if that is the case, then the next state is going to be live for that particular cell. That is good. Now the next third one is that any live cell with more than 3 live neighbors would die due to overpopulation. So okay, if the current state is live and if the number of neighbors is greater than 3, if that is the case, then basically the cell is going to die and the next state is going to be 0. And the last one is that if any dead cell with exactly 3 living neighbors would become a live cell because of reproduction. So if the current state is going to be 0 and if the number of neighbors is exactly 3, then the next state is going to be 1 for that particular neighbor. These are the only 4 rules that we are concerned with for our game of life, and initially we would be given an example that looks something like this, where on an m cross n grid we are given some values that represents live and dead cells, and we need to find the next subsequent states based on these 4 rules. So this is the whole ask of the problem. Now let's try to see some examples. So if we see this first example, okay, let's see that what would happen with each cell. So currently the position of this cell is 0. Okay, this is a dead cell. Let's see, for dead cell, does it has 3 neighbors that are alive? No, that is not the case, which means this will remain dead. Okay, so this will remain dead. Now for this next particular cell, okay, currently this is live 1. For the live cell, how many live neighbors this has? This only has 1 live neighbor, which means it is less than 2 live neighbor. So this would also be dead. So this is going to be dead. Also for this one, this is already dead, and again it will remain dead. And also this one will this one. Okay, so this is the important part. Now at this particular position, we do not need to see the positioning of the neighbor from this particular cell. We need to see the positioning of live neighbors from this original cell. So this is important for this problem. So even when we are at this position number 1 and we need to identify that how many number of live neighbors this has, we are going to refer over here, not on this newly created state, because all the states are going to change at the same time. Here I'm showing you one by one, but in originality it's going to happen everything at the same time. Okay, so in this case currently this one only has one live neighbor. So again this one has less than 2 live neighbors. So since the number of live neighbors is less than 2, this is also going to become 0. Now let's try to solve for this next problem. Okay, in this next one, okay, this one looks very similar, so I'm going to add one more one over here. Now in this case, okay, currently this one is 0. Let's see that how many live neighbors this cell has. This cell currently has 3 live neighbors. Okay, if there are 3 live neighbors, which means that this 0 state has the possibility to become state number 1. So in the next state, this is going to become value number 1. Okay, and in the over here, now this one has 2 live neighbors, not 3 live neighbors. We are not considering this portion, we are only considering the original pattern. So currently this one has 2 live neighbors. If there are 2 live neighbors, it will remain 1. So this will remain 1. Same goes with this one. This has 2 live neighbors, so this will also remain 1. And same goes with the last cell, that the last cell also has 2 live neighbors, so this is also going to remain 1. And this is going to be the next state. Let's try a little bit trickier example. So in this case, let's see that what is going to be the answer. And this is going to be the next state. And this is the whole crux of the problem that we need to solve. Now, understanding this problem is more trickier than actually solving this problem, because the solution for this problem is actually quite simple. And there are only like just few things we need to consider to make this more efficient. Okay, so now we have our example that we are going to use to solve this problem, and we have the number of rules that is already given in the problem statement. And now let's see that what is going to be the solution. Now suppose if we want to solve this problem, what are the things we are going to need? Well, first thing we are going to need is that for every single cell we are going to need the number of live neighbors. Okay, so we would be able to calculate that using just going over the grid, but in the problem we would be able to do it quite efficiently using just scanning through all the neighbors of any particular cell. So that is not a difficult task to do. Now let's see that what would be the solution. Now suppose we are at this particular position 1. Now how many number of live neighbors this has? This one currently has 2 live neighbors. Okay, if there are 2 live neighbors, this one is going to remain 1, so we don't need to do anything. Let's just keep this one as it is. Now for this particular one, this has 3 live neighbors. So again, we are going to use this rule. So this one is going to remain as it is. Now for this particular one, this also has 2 live neighbors. So we don't need to do anything. This one can remain as it is. So currently this upper row is going to remain as it is. Now for this particular 0, now this 0 is actually covered with all 3 ones, which means that this 0 needs to become a value number 1. Okay, so now this becomes value number 1. Now when we are at this position number 1, how many number of live neighbors does this particular one has? Well, okay, let's count. This one has 1, 2, 3 live neighbors. Okay, 4 live neighbors and also 5 live neighbors. The question is, can I call for this particular cell that it has 5 live neighbors? The answer is no. Why no? Because this particular one was originally a 0, and hence this should only have 4 live neighbors, not 5 live neighbors, because this cell I changed while I was iterating over. Now this is a problem that we have to worry about. And what is happening is that while we are iterating over the matrix, we are changing the state depending on these 4 rules, and it could be possible that the rules that are being changed could impact the remaining cells on their rules, and we might end up with a wrong answer. So one possible solution for that is that rather than making changes in place, if we just create a duplicated grid for this particular cell which contains the original items. So say for an example, suppose this was the original input we are given and we need to make changes. So what we are going to do is, first of all, we are going to create a duplicated entries and we are going to keep track of live neighbors. Okay, so let's just first quickly create a duplicated entry. If I create, okay, so now I have created a duplicated entry, and now whenever I have to make the change, I'm going to make change in this original box. But in order to find that how many number of live neighbors exist, I'm going to check on the box with the previous state. So this is going to be the copied version and this is going to be the original version. And after I'm done making change to all the original items, basically all I will have to do is just copy them over to the copied version, and then I would be able to calculate the next state of the original version. So that is how I'm solving the problem of state changing by creating a duplicated entry. Okay, and now this becomes very easy. How very easy? Okay, so we already iterated over this first row. The values are going to remain 1 1 1. That is common, that is good. Now we are at this current 0 position, so this one has 3 live neighbors, so definitely this is going to become 1. Okay, awesome. Now currently I am at this particular position 1, and the number of live neighbors is, it has 4 live neighbors. So because it has 4 live neighbors, it has greater than 3 live neighbors, this would become 0. So that this I can make change over here, that this would become 0. For this particular 0, how many live neighbors it has? It has 1 2 3 and 4 live neighbors. And now see over here, because I have this copied version, I was able to come up with the value number 4. If I was checking previously, I would have come up with the value number 3 and then I would have changed its state to 1. But actually, since this has 4 live neighbors, I would not need to do any changes to the state of this particular 0, and I can keep it as it is. Now I'm at this particular position 0. Okay, so for this 0, how many ones it has? It only has 1 neighbor, so I don't need to do anything. For this particular 0, how many neighbors it has? It currently has 2 neighbors, so I don't need to do anything. For this particular 1, how many neighbors it has? Currently it only has 1 live neighbor. Meanwhile over here it shows 0, but actually it has 1 live neighbor, so the number of live neighbors is less than 2, which means this state is going to be changed to value number 0. So let's see that from this particular original version we had, how many items got changed. Basically this got changed, so this became 0. This also got changed, so this was originally 0 and then it became 1, and this got changed. So this is how we would be able to solve the problem of game of life, just if we just create a copied version, and then it becomes very easy for us to find the live neighbors. Now the question is, your interviewer is directly going to jump onto you saying that if we see time and space complexity for this approach, the time complexity is going to be big O of m cross n. Why? Because we need to iterate over the entire grid to calculate the result. That makes sense. But if we see space complexity, the space complexity is also going to be big O of m cross n. Why? Because we are using this additional space to create a new copied matrix. And your interviewer is directly going to jump and saying that, can you solve this problem with big O of 1 space complexity? Can you do that? Okay, now let's see that how can we solve this problem using the constant space. For that, we are going to do some few modifications. And what are the modifications we are going to do? Well, first we will have to understand that what are the items we need. For any particular cell, we need the information of number of live neighbors it has. Okay, but we need this information on terms of like number of live neighbors in the original state. So now what would happen is that if we are at this particular position 0, this 0 would be changed to 1, and then when we come to this position, then we will try to find that how many number of live neighbors in the original state it had. Then we don't need to consider this particular value, so we need a way to somehow store its original state, and this can be done pretty easily. How? Basically currently we are dealing with integer values over here, so rather than using zeros and 1, what we are going to do is we can also use -1 and value number 2. And what would this -1 and value number 2 would represent? Well, it would represent is that if, say for an example, if the current state is 1, okay, so currently it is alive. Okay, if the current state is 1 and somehow it becomes dead, then in that case, rather than this 1 would have been converted to 0, we are decreasing the value, but rather than putting this as 0, we can actually put this as -1. And what would that do is, okay, so that means that this -1 should be dead. This is like we are using it as a placeholder, but this -1 would also indicate that the original state for this particular cell was actually 1. So when we are counting the live neighbors it originally had in the previous state, we would be able to calculate. Same way, if we are in a position where a dead state comes to life, So dead becomes alive if that happens. In that case, from 0 to, rather than going to 1, we would directly go to position number 2. And that is also another way that whenever we identify value number 2, we would presume that originally that was not live in the previous state whenever we are calculating the next value. So if we need to do that, we need to make some changes to our rules. And what is the change we are making? The change we are making is that anyhow, if the current state is live and if the next state needs to be dead, in that particular case, this is where we are going to put -1. So because this becomes dead, we are going to put this as -1. For this particular case, 1, if there are 2 and 3 live neighbors, this is going to remain 1. So we don't need to do any changes over here. For this particular one, if the number of neighbors is greater than 3, which means that this 1 would die. So this would also become -1. And for this particular 0, if the number of neighbors is 3, so in that case, this would become alive. So we would change the value to 2. So these are few rules we are changing. And now let's see that how can we make the things work out in place without using any additional memory. Okay. So this particular row we are not changing because we are implementing this particular rule. Now we are at this position number 0. So this 0 needs to be needs to bring back to alive. So if this is coming back to alive, rather than making this alive with value number 1, we are actually going to mark this as value number 2. So this would also indicate that if the value is 2, then the original state was 0, and this is going to be very helpful. Now we are at this position number 1. How many number of live neighbors it has? Okay, so currently it has 1, 2, 3 and 4 live neighbors, not this one, because the value is 2, which means that the previous state was actually 0. So we are not considering that. So since this has 4 live neighbors, so greater than 3 live neighbors, this needs to die. If this die, we are going to use this as -1. So that is going to be helpful to us in the future. So this becomes -1, which would indicate that the original state was actually 1, and this is going to be helpful. Now we are at this position number 0. How many number of live neighbors it has? So it currently has 1, 2, 3 and also 4 live neighbors, not 3, 4 live neighbors, because this 1 used to, this -1 represents that this used to be originally 1. Okay, so this would remain 0. Now again, for this particular 0, how many number of live neighbors it has? So currently it has, okay, so this was originally 0 and this was originally 1. So this only had 1 live neighbor, which means this would remain 0. Same goes for this one. This particular 0 has, okay, 1 live neighbor and also 2 live neighbors. So if there are 2 live neighbors, we don't need to do anything. And for this particular one, how many number of live neighbors it has? It only has 1 live neighbor, which was this value number -1. So this is going to turn out to value number 0. But rather than turning to value number 0, we are going to turn it to -1. And this is going to be the next state. Now, once we get this next state, this is not the answer we need to return, because for our game of life, we need to return all the cells in either 0 or 1. Either they are dead or they are alive, nothing more than that. So in that particular case, what we can do is, if at any point we identify the value to be like positive, so in this case this 2, so this needs to be converted to value number 1, because this indicates that this one is alive. And if we find 0 or negative value, which means that that one is dead, so in that case we will make these changes. So these two are going to become zeros and this one is going to become 1, and this is going to be the next state, and this is the whole solution. See how beautifully we are able to change everything by just simply making few changes to the input rules. And now if we see time and space complexity, in this case the time complexity is actually going to be big O of m cross n, because that is the grid size we will have to traverse. And if we see space complexity, the space complexity is going to be big O of 1, because apart from using like few variables, we are not using any additional space, and this is a very beautiful solution. Okay, so since this is already a pretty long video, I'm just going to explain you the code, and then I would post this code in the solution, so you would be able to check it out from there. Now, if we see, okay, initially we are initializing an array called neighbors, where we are adding the value 0, 1, -1, and this is going to help us navigate through neighbors of any particular cell. At the same time, we are getting the values of the row length and column length. So these are the values of m and n inside our grid. Now, first of all, we are creating two for loops, one inside the other, where this would allow us to iterate over the given input matrix cell by cell. After that, we are originally initializing a value of integer live neighbors, because this is the most important thing we need to consider, that how many live neighbors any particular cell has. And this is exactly what we are going to do next. We are going to run two loops, but this is going to be a finite number of cases we need to do. So this is not going to add any additional time complexity to our problem, but this is going to allow us to iterate over our neighbor. We are using this condition so we do not go out of bounds, and then at any given position, if we find that any particular neighboring cell has value number 1, then we are going to increment the number of live neighbors for that particular I and j positions. So this, okay, so this part gives us the number of live neighbors. That is pretty awesome. After that, now we are going to implement our 4 rules that we have established. And for these 4 rules, remember, first of all, we are going to check that if the given cell value is, if that is dead or alive. If the given cell is alive, then we are going to check that whether it has the number of live neighbors less than 2 or greater than 3. If that is the case, then the cell needs to die. And if the cell dies, we are going to change the value from 1 to -1. And if that is not the case, we will check that if the given cell is actually dead. If that is the case, which means we are going to check that if the number of live neighbors is exactly 3. If that is the case, which means the dead cell needs to be alive, and then we need to change its value from 0 to 2. So basically, this particular for loop is going to allow us to get all the values of the board setup with all the cells positions changed from either 0 to 2 or from 1 to -1. After getting that, all we need to do is just iterate over the given matrix again, and then simply check that if at any point we identify the value is going to be greater than 0, or the value is going to be either 1 or 2, which means we will need to convert that value back to 1, or else all the remaining values are going to be 0. And this is the whole solution. Pretty sweet and efficient, both in terms of time complexity and also in terms of space complexity. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code, and our code runs 100% faster than all the other solutions, which is pretty great. And I will be posting the solution in the comments, so you would be able to check it out from there. Also, there is one more place if you want to check all the coded solutions for many of the LeetCode problems that I have solved, and this is the GitHub repository that I have made public, that I will be posting this link in the description and also in the comments, so you can check it out from there. Let me know what do you think about this problem, and if there are any problems you want me to solve in the future. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do word search lead code problem, and if we see the number of companies where I want to work at who have already asked this question, there are companies like Amazon, Twitter, Microsoft, Uber, Bloomberg, Facebook, TikTok, Snapchat, Google, Apple, Samsung, Roblox, Goldman Sachs, ByteDance, and eBay. So these are really popular companies, and this problem is really popular because it has very real life applications. We have all played games like crosswords and Wordle on our phones and on the newspapers and different kinds of stuff. So that is where this problem is associated with, and we are going to see that how to solve this one. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given an m cross n grid of characters called board, and we are also given a string called word. Now we need to see that if this word can be created based on whatever the number of characters we are given on this board, and if it does, we need to return true, else we need to return false. Also, we are given a note that the word can be constructed from letters sequentially adjacent cells, where adjacent cells are either horizontally or vertically neighboring. And we are also told that same letter cell may not be used more than once in order to create that word. So let's try to understand this with an example. Over here we are given this big board, and on this big board we are told that we need to find the word A, B, C, C, E, D. So if we see over here on these marked values, so this starts with the word A, the neighboring word is B, the neighboring word is C. Again, we are told that we can horizontally or vertically see the words. So if we go vertically downwards, we see another C, and then we find another E, and at the end we find D, which is also adjacent to E, which is this letter, and this is basically part of this given board. So in this case we can return true.
Now suppose if this word if we were not able to construct this word, we would not return true and we would return false. So let's see that what would be the optimal approach to solve this problem. Well, we have actually solved similar problems like this in the past using DFS and backtracking, and this is what we are going to do for this problem as well. Let me quickly show you how. Okay, so suppose this is the custom example we are given, and we need to find the word spider to see that whether it exists on this given board or not. And the idea is actually quite simple. What we are going to do is, first of all, we are going to take the first character inside this word, which is S, and we are going to iterate over this matrix until we find this first character. The moment we find the first character from whatever the place is, then we will keep on trying to find the next letter, the next words inside this word, to see if it exists in the neighboring node or the neighboring cell of the board inside this given matrix. And if somehow we are able to reach to the end of this word, we can return true. If we don't reach the end of the word and we actually reach the end of the matrix, we can return false. So the idea is actually quite simple, and there are just few tweaks we will have to use in between. So first we will start iterating over this matrix, trying to find this word number S. Now this is not S, this is not S. Over here we find the first value as S. So because this is the first value as S, now we will have to try to see that whether this P exists or not in the neighboring node of this S. We can clearly see that P exists. But before doing that, what we are going to do is we are actually going to mark this node as visited. So one way to do is to use some visited hash set and store all the values, but that is just causing strain on and to have an extra memory usage. Rather than doing that, we are going to actually modify this input, and we are going to mark it something like hash or something, which is an invalid value and it can never be there. So which means at any point we encounter that this value is hash, we don't need to go back to that place. Now we will start iterating over the neighbors of this S. So neighbors of S can be these three places. If we try to look at these three places and we are looking for the alphabet P, so P is present over here, which means that so far we have found S and P. Now we will update our value to I, and we will try to look for I in this P's neighbor. Also we will mark this node P as like hash, so we don't come back to this place again. Now this P has only two neighbors because this neighbor S has already been visited because its value is hash, so we can't do anything about it. Now we are looking for this letter I, and we find the letter I over here, which means again we will mark this as hash. We will update the value of word we are looking for. The word we are looking for now is D. We'll try to find the neighbors of I, and in the neighbors of I, okay, we don't find anything over here. This is not D, and this has already been visited, which is hash, which means that there is no neighbor of I that contains this value D, which means that now we haven't found the word so far, and we still have matrix to go to that we haven't visited so far, which means that now we will backtrack from this I to the position we were originally at, which means that from this I we came from P, from this to this P we actually came from S, and now we can say that okay, even in this S it does not lead to us to find this word, and then we will again proceed with our search. So again we are trying to find this letter S again and not the D, because we did not find anything in the route, which means that now okay, this P is not S, this I is not S, this T is not S. So we are good so far. Now at this position we find a letter S, which means that okay, this S has been found. Now in the neighbor of this particular cell we will have to find the letter P, and we are going to mark this S as hash as a way to identify that this has been visited. Now what are the neighbors of S? These four are neighbors of S, and the one value we can find where the P exists is this one. So again we will repeat the same process. We will mark this as a hash. We'll try to find the word I we will find over here. So again we will mark this as a hash, and we will try to find D in the neighbor of this I. So we find D over here. So again we will mark this as hash. We will go update the word we are looking for, and now we will try to search for E inside these neighbors, and we can find it over here. Again mark this and then try to find this R. So R we actually find in the neighbor of this one, and this is the correct R. which means that now we are able to reach to the end of this word list, and we can return true in this case, saying that okay, this actually exists inside this given board, and we will be good. So this solution works perfectly fine. Let's see the time and space complexity with this one. So for the time complexity, actually the time complexity is a little bit tricky to find. Why? Because the time complexity is actually big O of n, which is the number of cells. So for every single cell we will have to iterate at least once. So n is given, but then we will have to repeat the same process for 3 times to the length of L in the worst case scenario. Why 3 times to the length of L? Because notice that at any single position, suppose we were at this position number D, and we need to see that okay, whether the next value E exists or not. So we need to check 3 places, not this one, because this already has the value hash, which means we won't check this one. But we in theory we might have to check at all 3 places, and imagine if all 3 of them had the value E, we might have to explore the paths on all 3 of them in order to find the next value R. So that is why at every single position N, we actually have 3 different options to see that whether this word exists or not, and this L is actually length of the given word. So that is why this is the time complexity. In terms of space complexity, we actually need to store the value inside our space until the time we reach to this entire word. So it would be big O of L, where L is the length of the word that is given. And this time and space complexity works perfectly fine, and I hope this solution makes sense to you. Let me quickly show you that what would be the coding for this one. So for this word search problem, we will actually have to create a backtrack public method that will call itself, and recursively we will try to achieve its answer. So there are some variables that we will need in both in this boolean exist method and also in the new backtrack method that we are trying to create. So let me define some variables that are global and that we can use in both the methods. And the variables we are going to create is to store the value of this board, and we will also need the row and column size of this given board character array. Now we have these, we will assign values to all these 3 variables from these given input endpoints. Once we have this, we will have to iterate over this board character array. So we are going to assign 2 for loops, and for both the for loops we are going to have the I and j value iterate up until the point of this rows and columns, and inside this for loop we will call our backtrack method. Now inside this for loop we are going to call our backtrack method, and we are going to have backtrack method return a boolean reply either true or false. And inside the backtrack method we are actually going to pass in the values of the current row position, current column position, word we are trying to find, and the index value we are currently at. So for the index value we would initially start with the position 0, and we would increment it every single time inside our backtrack method. And if at any case this returns true, we can simply return true in this case. And somehow if we are able to complete this loop and get out of it without returning true, which means word does not exist, so we can return false. Once this is done, now we will create our public boolean method called backtrack. Now first of all we will check that what is the condition where we will need to return true. So if at any point we identify that the index value is actually greater than or equal to word length, which means that we have already found that the current word already exists inside our given character array, so we can return true in this case. So now we will try to find the terminating conditions, and inside the terminating conditions, first of all we will check that whether the row and column position are they going out of bounds or not. If they are going out of bounds, we can return false immediately. If that is not the case, we will try to see that the current value we are looking at inside our board, if that value is not in sync with whatever the index value of the word we are looking for. If that is not the case, we can also return false immediately. So if any of these conditions are true, we can return false immediately. None of these conditions are true, which means that the current index value actually matches the value of that row and column position inside the board, and now we will have to iterate over the neighbors of this current row and column value inside the board. So in order to iterate over the values of the row and column, we are actually going to have two arrays called row direction and column direction, and that will help us navigate all the neighbors of any particular cell. Also, before moving to the next element, we are going to mark the current row and column position to have a value called hash, so we avoid checking the same element twice. Okay, once this is done, we will also have a boolean variable called return, and initially we are going to initialize its value to false, because basically we are going to call the backtrack function for all the four neighbors of the current cell. So for that we will keep track of this ret variable, and we are going to run a loop to iterate over all the directions, and we will add the values of these row direction and column direction to subsequent row and column positions inside this recursive call to our backtrack function. We will also update the value of the index, because we can determine that we have already find the word inside the previous index, and that's why we are calling the next index where value to be searched inside the neighbors of any given row and column position. And also at any point, if we identify that the answer of this return function is actually, or this return variable is actually true, we can break out of that particular element immediately, and we don't have to check all the other neighbors. So we will put that condition as well. Once that is done, basically we are done with the checking part. Now the only thing we need to do is we will have to update the value of the row and column position to whatever the value that was originally there, and in the end we can simply return whatever the answer we got for this ret function. This is pretty much it for both our backtrack method and also our main method, and this should be able to solve our problem. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code, and our solution works as expected. And I would be posting this in the comments, so you can check it out, the solution from there.
And my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do a very interesting LeetCode problem called valid Sudoku. Now, if we see some of the popular companies who have already asked this question, there are companies like Amazon, Apple, Nvidia, Uber, Microsoft, Facebook, Google, Bloomberg, DoorDash, Goldman Sachs, and Snapchat. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well-liked problem on LeetCode. In this problem, basically we are given a 9x9 Sudoku board, and we need to determine that whether this given Sudoku board, if that is valid or not. Now, we are told that only filled cells needs to be validated according to following rules, and we are given 3 rules to determine that whether the board is valid or not. First rule dictates that each row must contains the digits between 1 to 9 without repetition. This is the key phrase, that there should not be any duplication. First rule defines that every single row must have unique characters from 1 to 9. Second row defines that every single column must have unique characters between 1 to 9. The third definition shows that the box of 3 by 3 or the sub boxes in the grid must contains the digit 1 to 9 without repetition. So this is a little bit tricky one, but basically amongst the 9 by 9 box, we can make 9 different 3 by 3 boxes where the values 1 to 9 should be present without any repetition. Now we are told that the Sudoku board in this case is partially filled, and we need to only check the boards based on the filled items, nothing more than that. So it could be possible that we cannot be able to complete the entire Sudoku, but given the filled elements, if they are at least behaving these 3 definitions that are mentioned, where every single row, every single column, and every single box, they all should have 1 to 9 unique elements, then we can determine that this Sudoku board is valid. If it is not the case, then we can determine that this is not valid. So if we take a look at this particular example, this is the example of a valid Sudoku box. And what makes this Sudoku box valid is that every single row, or all amongst all the 9 rows, the filled elements are filled in a manner that there is no repetition between 1 to 9. Now if we just take one example, say for example for this first particular row, if I add one more 5 over here, then it completely makes this Sudoku board invalid, because the elements 5 is repeated 2 times in this particular row. We are not concerned with the empty cells, because we can determine that can have any particular value, but if there is a 5 or any duplication present over here, we can determine this to be invalid. But let's just say that 5 is not present over here, so we are good. Same way, if I just put an 8 over here in this middle portion, then this column would be invalid, and that would make this entire Sudoku box invalid. So that is also one more thing that we need to take care of. And the third and little bit more complicated thing is the boxes that we need to be concerned with in this case. So there, as we can see from this image, there are actually 9 boxes present in any given Sudoku board, and we need to determine that 1 to 9 values are remain non-duplicated for all of them. So basically, say for an example, for this particular box, now this box currently only has one value 6, which means this box is valid because there is no duplication. But if I add one more 6 over here, which means then the 6 is repeated 2 times, so that would make it invalidated. So basically we need to take care of rows, we need to take care of columns, and we need to take care of boxes for this particular problem to solve them. Basically, I'm going to show you 3 different solutions, one for the row, one for the column, one for the boxes, and then we will find a way to combine all 3 of them. So say for example, this is the row we are given, right? Now we are only considering one row for now, because same solution can be applied to all the remaining 9 rows. So that is a trivial fact. So basically, first we will try to determine, suppose this is the row we are given. What is our objective? Our objective is to make sure that all the filled values over here, they are unique between 1 to 9 and there is no repetition. So the simplest way to do is to create a hash set. So if I create a hash set, currently this hash set is empty. Maximum possible length this can have is going to be 9, because there are only 9 cells in any given row. Okay, now the logic we are going to use is that first we are going to iterate over the row. If the value, there is some value, we will try to first check that whether that value is present in the hash set or not. If it is not present, then we will add that particular value in the hash set and move on to the next element. If the value is already present, which means that there is a duplication we find, and then we can simply return false, that this given Sudoku board is invalid. So let's try to do that. First we are at position number 1. Currently there is nothing in the hash set, so because there is no value, we will add entry 1 over here, and we can determine that this node has been visited, or this cell has been visited for the row perspective, and there is nothing wrong we find. Now this one is a dot. So if there is a dot, or if there are no values, we can simply skip over that, because that is none of our concern. We are only concerned with the elements that are already filled. Now the next element is 3. So we will add an entry 3 over here, because 3 was already not present. This one is again empty. This one is value number 6. So we will add 6 over here, and then same way we will add 2 over here. And these 2 cells are not empty. So we have reached to the end of the row, which means we can determine that this particular row is currently valid and there are no issues with that. But say for an example, for this last cell, rather than adding this value, if we had one more value number 3 over here, then what would happen? Once at this position, when we add value number 2 over here, now we are over here. This one is a filled value. Because this is a filled value, we will try to see that whether this value is present in the hash set or not. Since this value is already present, this is a big no-no, and we found a duplicated entry, which means immediately we can call this entire Sudoku board invalid, because we find an invalid row. So that is how we are going to determine the rows. Now currently this one only had one row, so we use just one single hash set. Say for an example, we were dealing with 9 different rows. If that was the case, what we would have to do is we would simply have to create 9 different hash sets, and basically for every single hash set we are going to repeat the same process. So this is just repeating the same process for different set of inputs. If the given Sudoku board is, let's say, 16 by 16, we would have had 16 hash sets, but still the core concept would remain same. Now the way we've solved for the box, the same way we can actually solve for the columns. Again, for the columns, we are also going to create a hash set. So say for an example, this is the column. We will create the hash set and we will repeat the same logic. So currently this value number 1 is not present, we will add value number 1 over here. This 3 is not present, we will add 3, same way we will add 6, and we will add 2. And now we are at the end of this column and we didn't find any duplicated entries. So we can say that this particular column is valid, and then we can move on to the next column. And same way for the next column, we would create a new hash set. And if any point in time we find duplicated entries, so say for example, for the second column, we have two values 1 and 1 over here. First we would add this 1 over here. Then the moment we move on to the next value and we see that, hey, in the hash set 1 is already present, we can say that, okay, this particular column is invalid, and that is why this entire Sudoku board is invalid. So this is also a very simple thing to understand. Same logic we are using, what we use for rows, we are going to use for the columns. The thing is for the box. Now for the box, this is a matrix kind of a structure, okay? And for the matrix kind of a structure, again, our main logic or the thing we need to achieve is going to remain the same, that we need to make sure that there are no duplicated entries for the filled values between 1 to 9. So again, even for the box, we would be able to create a simple matrix or a simple hash set. Now for this even hash set, we are going to apply the same logic, and we would keep adding the entries until we find any duplicate entries. And if we find duplicated entries, we will call it invalid. So this is a very simple thing to do, but the tricky part is, okay, now say for an example, we need to determine for rows and columns. Okay, currently say for an example, we are just ignoring the boxes for now. We are only considering that how to solve this problem for just row and columns, and we need to find that we don't find any duplication between 1 to 9 for every single row and every single column. How we are going to achieve that? We are going to achieve that in the same manner I explained earlier. The only logic we are going to use is that we are going to create 9 hash sets for rows. Okay, so for rows we are going to create 9 hash sets. Every single row we are going to check for the duplicated entries. If we find any duplication, we can return invalid immediately. If we don't find the duplication, we will move on to the next row, and we will keep on repeating the same process. The same thing we are going to use for the columns as well, that even for the columns we are going to create 9 hash sets. So again, and we are going to repeat the same process to check that whether there are any duplicated entries or not. And since there are none in this particular case, we can simply in the end return the answer valid. Now remember, we only solve this problem for the rows and columns, okay? But the thing is, we need to take care of the boxes as well. Now for the boxes, there is just one tricky part, and the tricky part is that actually for the boxes, it is not as simple as just the correlation between row and column. Because for rows, we had the particular separate entries for every single row that we can traverse over them or determine them pretty easily. Even for the columns, we have the direct way to identify that whether this is a column or not. But when it comes to the boxes, we need to establish a correlation between the set of different rows and different columns. And how would we be able to achieve that? Okay, so even for the boxes, basically we need to create 9 hash sets. But the thing is, how do we define which number goes where? So basically these are going to be all the boxes that we need to create, okay? And these are the 9 boxes. But the thing is, how do we able to define the 9 boxes? The answer is quite simple. We are actually going to do a division by 3 for any particular row value and any particular column value. So that would be a very clear indicator on what box we need to choose. And let me give you a quick demo. So basically the idea is that, okay, currently this row position is 0, 1 and 2, okay? Now say for example, if we do like 0 divided by 3, what is the value we are going to get? 0, of course. If we do like 1 divided by 3, what is the value we are going to do? We are actually going to consider the floor value, okay, not the ceiling value. So if we consider the floor value, 1 divided by 3 is going to be like 0.33. So basically in the integer it is going to be 0. So these 3 values are going to represent 0. Same way these 3 values are going to represent 0, which means if we are iterating over any of these cells, we can say that we need to consider box number 0 for that. So that is pretty good. Same way, if we are going over any other these 3 values, so okay, this is going to be 1, 1 and 1, because if we divide them by 3, and same way this is going to be 1, 1, 1, because if we divide them by 3, same way this is going to be 2, 2, 2, and same way this is going to be 2, 2, 2. Now say for example, we are at any cell amongst this particular box. Now we need to identify that which particular hash set to select. Now this one is going to be box number 6. So hash set number 6 we need to select. Okay, but how do we define this hash set number 6 is going to be the correct one? And this is where we are going to use this formula, where for any particular cell position we are going to do this formula where we are doing row divided by 3 plus we are doing 3 and plus we are doing column divided by 3. Okay, so this is the formula we are going to use to determine that what is the correct box number. Now suppose for this particular formula, suppose we are at this particular box or this particular cell. Okay, now if we take a look at this particular cell, currently the row is going to be row number 4. Okay, row is 4 and currently the column position is going to be 7. Let's apply this particular formula for this row and column position. If we do that, we are going to do 4 divided by 3 plus 7 divided by 3. Okay, so in this case 4 divided by 3 is going to give us the answer number 1, plus 3 and plus 7 divided by 3 is going to give us the answer 2. If we do sum of these three values, we are going to get the value of 6. And the 6 is going to determine that the box currently, if we are at this particular position, we need to check it against hash set number 6. This is the only complicated matter for this particular question. If you are able to identify a way to find the correct box, then this is a very simple problem to solve, and which we just did. So this is the whole logic. And basically now we know that how we are going to solve for row plus column plus box. The idea is that for row we are going to use 9 hash sets, for column we are going to use 9 hash sets, and even for boxes we are going to use 9 hash sets. And we already know how to determine what is the correct box we need to look at, and based on that we simply need to check for the duplicated entries. If we find any duplication, we simply get rid of it. If we don't find any duplication, awesome, then we can conclude this given Sudoku to be valid. And this is the whole optimal solution. Now if we see time and space complexity for this one, the time complexity is actually obviously going to be big O of n square. And why n square? Because we are given n to be same for both rows and columns, so that is why this is going to be big O of n square. If we see space complexity, now this one is like a debatable question, because we already know that we are going to use 27 additional hash sets. The thing is, why did we come up with this number 9? Because we are given n is equal to 9 by 9 matrix, so we are given n is equal to 9, so that is why this 9 came in. So basically space complexity is going to be big O of 3n. So in general we can write this to be big O of n. But if we are explicitly told that we are only going to use 9 boxes, then we can also conclude this to be a finite number, and this could also be considered as constant. So if you do this discussion with your interviewer, you are going to look very clear in your concepts regarding time and space complexity. Since this is already pretty long video and the coding is just a bunch of repetition, so I am just going to explain you the code and then I'm going to paste this in the comments so you can check it out from there. So first of all, we are going to create an array of hash sets. So first we are going to create an array for row, second we are going to create for column, and third we are going to create for the boxes. And the size of this particular array is going to be the size of 9 that is given over here, and we are hard coding this value because we are basically told that this is going to be a 9 cross 9 Sudoku. Now after filling these values, we simply need to initiate the hash set for every single one of them. So we are going to just iterate over all the values, and we are going to initiate the hash set to accept the character as the input. Now we are going to run two loops. First is to iterate over the row, and second one is to iterate over the column. And using the two inner loops, like one inside the other, we would be able to iterate over the given input matrix. Now the moment we are iterating over the given input matrix, first of all we are going to determine that what is the current character at any particular position or any particular cell. Now if the value is dot, or if there is no value, we can simply continue and move on to the next element. But if there is a value, we are simply going to first do these things. First we are going to check that whether for this particular row hash set, is this value already present. If the value is already present, we can simply return false. If that is not present, we are going to add the value to that particular row hash set. Same thing we are going to do for the column, that if the value is present, we are going to return false. If the value is not present, we are going to add that value to that particular subsequent columns hash set. And then we are going to apply our formula where we are going to check for the particular box, and then we are going to check that for that particular box, if the value is present, we are going to return false. If it is not present, we are going to return the subsequent correct value. And basically, if we get out of the loop, we are simply going to return true, that we did not find any place where there was invalidity and we could have written false. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs decently fast compared to a lot of other solutions in terms of time complexity, and also it is very convenient in terms of space complexity. So I would be posting this solution in the comments so you can check it out from there. Also, at the same time, if you want to check all the solutions that I have done so far, I have created a public GitHub repository where I'm putting all of my answer, and this is going to be a great resource for anyone who is trying to prepare for different tech interviews. So I would be pasting this link in the comments as well, so you can check it out from there. Thank you.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do rotate image lead code problem, and this problem actually has very real practical applications, as we know that there are a bunch of different softwares that allows the option to rotate an image. And if we see the list of companies where I want to join in and already have asked this problem, there are companies like Facebook, Microsoft, Amazon, Apple, Google, Bloomberg, Uber, TikTok, Nvidia, eBay, Paytm, and Robinhood. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem, and basically we are given an n cross n 2D matrix which represents an image. Now we need to rotate this image by 90 degrees clockwise. Also, one more thing that is mentioned, that we need to do it in place. We do not need to use an additional 2D matrix to solve this problem. So the space complexity has to be constant in this case. Let's try to see it with an example. So over here we are given a matrix like 1 2 3 4 5 6 7 8 9, and we can see that this particular row is actually converted to this column, which means that all the nodes have been transported to 90 degrees, which means this 1 has gone to this place, this 2 has gone to this place, and this 3 has actually gone to this place. And same goes for all the other elements, that this 4 has actually gone to this place, which we can see over here, and this 7 has actually gone to this place, which we can see over here. And the same way it is shown in this second example. Okay, suppose this is the input matrix we are given, which means that this is the answer for the 90 degrees rotated matrix. Now notice couple of interesting things in both of them. Well, over here the value 1 2 3 is in a row. So over here this value 1 2 3 is actually in a column. Same goes over here, that this value 4 5 6 is in a row, but this 4 5 6 is in a column, and same goes for the 7 8 9 7 8 9. So this is clearly a pattern over here. And basically what we can do it is that if we somehow convert this input to replace all the values that are inside the rows to be inside the columns, and then reverse those entries, so reverse all the rows, we would actually get a 90 degree rotated array. And let me quickly show you how we are going to do it. Okay, so suppose this is the original input. I have drawn it much bigger over here, and now what we are going to do is, for every single row we are going to place it inside the column, and every single column we are going to place it in the row, which means that currently at if we consider this position number 2, if we see the I and jth location, this 2 is actually located at the position 0 1, representing these two values. So what we are going to do is we are going to flip the values of the 0 and 1, and same we are going to do this for this 4, which means that this 4 will come to this place and this 2 will come to this place. The thing they did for this 2 and 4 we are going to repeat for all the other characters, and then we would have an array which would have where all the rows would have been converted to all the columns. Also, there is a name for the process of converting all the rows to all the columns, and that is actually called transposing a matrix. So first of all, we are going to transpose this original given input matrix, and we will see that the result would look something like this. So this 1 will remain at the same position because this 0 0 is at the correct place, so we can't change anything. Now this 2 is going to be replaced by this 4, which means that over here we would have 2 and over here we would have 4. Again this 3 is going to replace by this 7, so over here we would have 7 and over here we would have 3. So if we just notice right now, this row 1 2 3 has actually been converted to a column, and this column 1 4 7 has actually been converted to a row. We are going to repeat the same process now, and now this 5 will not have any impact because the position is actually 1 1. But for the 6 and 8 we will actually have to swap their values, that now over here we would have the value number 8 and over here we would have value number 6, and this 9 will remain at the same position because the value is 2 2, which means we can't do much about it. And now basically now we have created all the rows and converted them to different columns. Now the next idea is that we are going to put this in the reverse order, and if we reverse the rows for this transposed matrix, we can clearly see that we would get a 90-degree rotated answer. Let's do that. So over here the values would be 7 4 1. If we reverse this particular row, same thing we will do for this one. So the answer is going to be 8 5 2, and again for this one, the last row, the answer is going to be 9 6 3. And if we see, this is actually same as the answer we had achieved before, and I just draw all these 3 different matrices to give you an example that how we are going to do the things. But basically all of this activity can be done in place inside the single matrix. All we will have to do is we'll have to use a temporary variable to first of all swap the elements in this fashion, and then once that is done, we will need a temporary variable to replace the values inside the given matrix and reverse the rows. If we see the time and space complexity for this approach, basically for the time complexity, we will have to iterate over all the elements inside the given node to create this transpose matrix, and once the transpose matrix has been created, we will have to reverse all the elements, which means that the time complexity in this case is going to be big O of n cross n, but we will have to repeat this process 2 times. So which means we can say that big O of n cross n times 2, but in general we can just write it as big O of n cross n, and this would be our solution. In terms of space complexity, as mentioned earlier, we are not using any additional space, which means we are doing it in a constant space complexity, and this is a very good solution. Any interviewer would be really impressed with your approach, and this works for all the different n cross n matrix. Now let me quickly show you another solution for the same problem where we don't need to do like this transposing activity, and we can actually solve this problem in a single go. So for the second approach, we are going to do things a little bit differently. First of all, I have drawn over here a bunch of different matrix of different n size. So n is equal to 1, 2, 3 and 4 I have shown you. And now we are going to see that if we rotate them 90 degrees, can we see some patterns over here? So suppose we have a matrix of the size number 1. If we rotate this 90 degrees, it makes no sense. The value is going to still remain same. So we are going to keep it as 1. Now for this n is equal to 2, if we rotate this matrix by 90 degrees, actually the thing is going to happen is that this 1 node is going to shift 1 value to the right, this 2 node is also going to shift one value to the right, 4 and 3, all of them are going to shift 1 value to the right, and the answer in this case is going to be, okay, so first of all we'll shift 1 over here, 1 value to the right, 2 and then 4 and then 3. So this is the 90 degrees rotated angle for this n is equal to 2. So basically what we have done is we have rotated all the values one place to the right, okay, for the outer layer. And in this case, since we only have 4 elements, which means the layer is only 1, we are good. So when we get to this n is equal to 3, things becomes a little bit interesting. And interesting how? Because we have the cells located on the outer layer and we have one cell that is located in the inner layer. Now when n is equal to 1, when the number of cell that is located inside the inner layer, we know that the value is going to remain same. So even if we 90 degree rotate this particular element, it is still going to fall over here on the same place. We are not going to do anything special with this one. But for these other values, we will going to apply the same logic we applied over here, where because n was 2, we had to rotate all the values 1 degree to the right or one place to the right. In this case, because n is equal to 3, we are going to rotate all the values to the two elements to the right, okay, and this would be the answer. So if we see in this case, this 1 is going to come at this place, this 2 is going to come at this place, this 3 is going to come at this place, and same thing is going to keep on repeating for all the other elements. And that is how we are going to find its solution. So let me quickly draw the solution for this outer layer over here. This is the answer for the outer layer of this matrix. And because in the inner layer we only have one element, and for one element we don't have to do anything special, the 5 is going to be at the same place, and this is going to be the solution, that we rotated all the elements couple of places to the right. Now in this case n is equal to 4. So obviously for the outer layer you can imagine that the pattern we are going to follow is going to be the same, that we are going to rotate all the elements 3 steps to the right. Okay, so that is clear. But for this inner layer, we can actually see that this time we have a set of 4 values, which means we have a 2 cross 2 matrix inside. So over here we are going to use the same logic we used over here, where we are going to rotate them 1 step on the right. So first let's do it for the outer layer, and then we will do it for the inner layer. So the rotation for this outer layer is completed. Now for this inner layer we will have to rotate them 1 times based on whatever we have seen when n was 2. So we are going to do the same thing. This is the answer of 90-degree rotated angle, which means one thing we can see over here is that we can have 4 pointers starting at this 1, 4, 16 and 13, and rotate all these values in place by using a temporary variable. Once that is done, we can repeat the same process for this value number 2, 8, 15 and 9, and again we will keep on rotating them sequentially at the same time in place, and then we would be able to fill out our outer layer. Once that is done, we will come inwards and we will start filling the inner layer based on whatever the number of n we have. And that is the approach we are going to take. Okay, so suppose we have a 3 by 3 matrix, and I'm going to show you what is the approach we are planning to take. Now this additional matrix I have drawn, that is only for the understanding purpose. Actually we are going to do everything in just one single matrix, but I'm just going to show you that what are the value changes happening and how we are going to use this temporary variable to fix our problem. So first of all, we are going to store the value of this 1 inside our temporary variables. Okay, so the value inside the temporary variable is 1. Now what we are going to do is, first of all, we are going to project this value number 7 to this place 1. So this becomes 7 and this becomes 7. Currently this is the scenario. Now we are going to project this value number 9 over here, which means that this 7 is going to be replaced by value number 9, and this is also 9 at this at the current moment. Again we are going to project this 3 to this 9, which means that the value of this 9 is going to be replaced by 3, and this is going to remain 3. And now at the final moment we are going to take whatever the temporary variable we had and we are going to put it in this place, which means that this value is going to be 1. So at a single iteration we have actually shifted values of all of these 4 places in its correct position. Again we are going to repeat the same procedure for these 4 values, which means that over here now we are in the next iteration. Now the value of the temporary variable is 2. Now because the value of the temporary variable is 2, first of all we are going to project this value number 4 to this place number 2, which means that currently both values are going to be 4, 4. Then we will project this value 8 to this 4, which means that this is already 8 and this value becomes 8. Then we will project whatever value of 6 we had at this position number 8, which means that this value would become 6, and this is already 6. And at the end we are going to take whatever the temporary variable we had, we are going to project that value over here, which means that this 6 is going to be replaced by this value number 2. And once that is done, essentially in 2 iterations we have taken care of all the values that were placed out in the outer layer, and we are done with this one. Now only thing we need to consider is this inner layer, and because for the inner layer n is equal to 1, which means that we can basically leave the value as it is, and this is the answer. And this is how we are going to able to rotate the entire element in 90 degrees in just like very few iterations. We don't have to do like transpose matrix and then replace all the values and change all the values. So even if we see the time and space complexity, in this case the time complexity is going to be big O of n cross n, but we only have to do it single times, and space complexity is going to be big O of 1 because we are only using an additional temporary variable to store some values. Apart from that, we are not using anything special to store any values. So we will initialize a variable called n, and we are going to store the length of the matrix for this one. Once we have that, we will have to iterate over this given matrix, and we are going to create 2 for loops to iterate over this given matrix. Now remember, we only have to iterate over half of the matrix. We don't have to do much work, which means that we are not going to iterate from int I is equal to 0 to I is equal to n. We are actually going to do it I is less than or equal to n plus 1 by 2. Now you will ask that why n plus 1 by 2? Because in the condition where the given n is odd number, we will have to take care of that scenario as well. So first of all, we are going to create a temporary variable, and we are going to store value of one of the elements inside this temp variable, and then we will start working on the flip operation for the remaining 3 elements. Once that is done, we will start iterating over all the elements. And once this loop ends, basically we would have rotated our matrix 90 degrees angle for all the elements. Now the question comes that how did I get this value of I and j? Actually, I could explain it to you, but I would expect that you draw the any 3x3 or 4x4 matrix on paper and try to see that how we are getting these values of I and j, because that would be a very good exercise for you. Anyways, I would be posting this code in the solution, so you would be able to check it out. But still, I would expect that if you do it by yourself, you would never be able to forget it. Now let's try to run this code. Okay, seems like our code is working. Let's try to submit this code. And tada, our solution is actually 100% faster than a lot of other solutions, and basically we are solving this problem pretty efficiently. Again, I would be posting this in the comments so you can check it out from there, and there I would ask you to figure out that how we are getting these values of I and j compared to this value of n, and that would be a really good exercise for you to do at home. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do spiral matrix lead code problem, and this problem has been asked by tons of my favorite companies. Companies like Microsoft, Amazon, Apple, Facebook, Google, Adobe, Uber, Bloomberg, TikTok, Walmart, Tesla, Paytm, Flipkart, ByteDance, eBay, Goldman Sachs, Robinhood, and Salesforce. So you can imagine that this problem has been really popular at top tier IT companies, and that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given an m cross n matrix, and we need to return all the elements inside the matrix in a spiral order. So suppose we are given matrix like this in a 3x3 matrix, we need to iterate over this given matrix in this following fashion in a spiral and return elements in that sequence. So to make things more understandable, I have drawn different matrix of different sizes, and let's see that what would be the spiral traversal for each one of them. So we will always start at the 0, 0 position, and then we will start traversing on the right side until we hit a boundary. So over here we hit a boundary, and then because we hit a boundary, we'll go downwards. Now again downwards we hit a boundary again we will go in the left direction. Again we hit a boundary over here of the matrix. Now we'll again go upwards in the direction, but now this time we will not wait for us to hit a boundary. We will actually stop at this position number 4. Why? Because if we keep going in this upwards direction, we will end up at this position number 1, which is, though it is before the boundary, still this is the node that has already been visited, which means that we are traversing in a particular direction until the point where whether we hit a boundary or we hit a visited node. So this is a really important concept to understand. Now let's go back to the traversal. So again from this 4 we will come back at this point 5, and now from this 5 you can realize that there is no other direction this 5 can go to, and this would be the answer. So this would be the end of the traversal. Let's do the traversal for this 4x4 matrix. So again we start at this initial position, we start going on the right direction, then again we go downwards, again we go leftwards, then we go up until the point when we hit this visited node. Again we go right, again we go down, and again we go left, and this would be the traversal. For this 5x5, let me quickly show you what would be the traversal, and of course it's pretty simple to understand, so I know you also know that what would be the traversal. This is how we are traversing in all three of the cases. Now remember that there are two important things to consider over here. First thing is that at any point we are traversing, we are always following a pattern in terms of the number of directions or the type of direction we are taking, and that pattern is always we start at the initial position, which is this one, and then we always go on the right side first. After going the right direction, we go downwards. So we go downwards. After going downwards, we go leftwards, and after going leftwards, again we go in the up direction. So we go upwards. Then again we go back on the rightwards. Again we go down, and again we go left and right up, and we keep on following until we reach to a point where all the nodes that are adjacent to any particular node. So in this case, this number 10, where all the other nodes they have already been visited. In this case, it would be this node number 13, where all the other nodes they have already been visited. So we are traversing until the point where we exhaust out of all the nodes that we can traverse. And let's see that what would be the approach for us to solve this problem. Like we already know that what are the directions we need to traverse into, and we are always traversing in any particular direction until the point where either we hit a boundary or we hit a visited node, which means that these things are important for us to keep track of, that this boundary or this visited node. We need to understand that how to identify them, how to keep track of them, and what are the different approaches to tackle both of these, and what would be the solution. So in order to solve this problem, there are actually two different solutions. I'm showing you both of them. You can pick whatever you want to. Both have its pros and cons, and you can discuss it with your interviewer which solution you want to pick. So let's go with the first one. Now first approach is that we actually start shrinking the boundaries and we don't care about visited nodes. How we are going to do it, let me quickly show it to you. So first of all, we always start at this initial position. We know the directions we need to take. We go right, then we go down, then we go left, and then again we go up. This is the state of direction we are going to follow. Let me also create our answer of the nodes that we are going to traverse along. So first of all, we start at this position number 1, and then we follow up until this point where we hit a boundary over here. Now the moment we hit a boundary over here, we are going to add all of these values to our answer. So let me quickly add all the nodes to my answer. And then because we hit a boundary over here and this was the direction, right direction, we know that next direction we need to go is downwards. So we start going downwards, but we are going to do one thing important over here, and that thing we are going to do is we are going to ignore all of them, and we are going to actually shrink our boundary up until this point. So originally this matrix was actually 4 by 4 matrix. Now we are going to convert this matrix to be a 3 by 4 matrix, and we are going to ignore this first row as if that never actually bothered and that never actually existed. So by doing so, what we are doing is that we don't need to take care of these elements, and since we have already added them to our answer, so they are always going to be in our answer as well, right? Now again we go downwards in the same path until the point where we hit a boundary. So we hit a boundary over here. We are going to add all the nodes to our answer. So nodes would be 8, 12 and 16 in this sequence, and again we are going to ignore all of them because we have seen all of them, and now again we are going to shrink our boundary up until this point, and we are going to ignore all of these places. So let me actually remove them, that they never existed for us. Now again, after downwards we will start traversing on the left direction. So we go until this point. We will add all the entries in our answer, and again we are going to delete all of them because they never existed for us, and our boundary actually shrinks even further. And after that we start going in the upwards direction. But notice over here we don't have to care about these nodes because we have already shrunk our boundary to only consider up until this point, which means that we are going to add this values 9 and 5 and again shrink our boundary, and then we will add this value 6 and 7, again shrink our boundary, add value number 11 and then again shrink our boundary, and in the end we are only left with one value, value number 10, and we will add it to our answer, and this would be the answer that we need to return. So this solution works perfectly fine. We don't have to bother keeping track of the number of nodes visited because we are shrinking our boundary with every single iteration. And let's see that what are the pros and cons of this one. So first of all, we'll try to calculate that what is the time and space complexity for this one. So time complexity is actually going to be big O of m cross n. Why m cross n? Because we have to iterate all the nodes inside the given matrix. So that is a given thing. Now in terms of space complexity, we are actually doing it in a constant space complexity. Like you can't consider this answer to be a space complexity because anyways we have to return a list of all the nodes that we have traversed. So that is part of the answer, that is not part of our algorithm, and that is why this is a very good approach. And you can discuss with your interviewer that if he is okay with this approach, you can also move forward with this one. Let me show you what would be the second approach. So for the second approach, we are actually going to keep track of the visited cells and also the boundaries, and whichever we hit first, we are actually going to change our direction. So one thing remains common is that we are always going to traverse in the same sequence of direction. So first of all, we will traverse in the right direction, then we will go in the downwards path, then we will go in the leftwards path, and then we will go on the upwards path. So this will remain common, and then we keep on repeating, and at any moment we hit either a visited cell or we hit a boundary. So originally we are at this position number 1, and we are going to mark all the coordinates of the matrix. So the coordinates of the matrix is going to be 0 1 2 3 and 0 1 2 3. Now current position of this 1 is actually 0 0, we can see over here. So what we are going to do is we are going to create a hash set, and inside the hash set we are going to first of all check that whether the coordinate that we are visiting, have we visited it already or not. If we have not visited it, we will add an entry to our hash set. So at this position number 1, we will add an entry to our hash set saying that okay, currently we have already visited this coordinate number 0 0, and we are also going to create our answer list, and inside the answer list we are going to mention all the nodes that we have traversed which we need to return in the end. So we will add this entry number 1, and then we will keep iterating on this direction on the right side until we hit either a boundary or a visited node. Remember, either a boundary or a visited node, both the things we are keeping track of. So and at the same time we are going to add all the entries. So in this case we would have added entries like 0 0 0 1 0 2 and 0 3. All the things we have added, we have already also added it to our answer that we have already traversed this nodes 1 2 3 and 4. And now we know that because we have hit a boundary, it is time for us to go in the downwards direction. So again we will go in the downwards direction until the point we hit a boundary, and we would have also added all the values to our hash set as well again, and also to our answer list as well. Like I am not going to bother writing all of them, but I can understand that you are smart enough to understand that. Again we go on the leftwards direction until the point we hit a boundary, and again we start going on the upwards direction. But notice that when we are going in the upwards direction, we are actually going up until this point number 5. We are adding all the values to our hash set, we are also adding all the values to our answer. Now at this 5, when we try to go this position number 1, we would first check that okay, whether this position number 1, which is located at the coordinate 0 0, have we visited it already or not. And we would identify that okay, the 0 0 has already been visited, which means that because it has been visited, we actually don't need to go and do that again. Or what we need to do is change our direction. So from this position number 5, again we would change our direction in the same manner where we would have changed our direction if we would have encountered any boundary. So then again we will add all those entries 6 and 7 and again add them to our hash set, and then we keep iterating until we reach to the end of all the entire matrix, and we would have visited all of them. Now this solution works perfectly fine. Now but the thing is, you would immediately say that hey, this solution actually we are using an additional hash set, which means that for the space complexity we are actually using big O of m cross n space complexity, which means how come this solution can be better. This is actually a bad solution. So your interviewer is definitely going to let you know that okay, you can't use this hash set to keep track of all the visited nodes. In this case, what we are going to do is there is another solution to solve this problem without keeping track of all of the visited number of nodes. So at any position, if we have visited some node, what we are going to do is we are going to add it to our answer list first, and then we are going to change its value. And how we are going to change its values, we are going to put something random that is out of bounds, or it doesn't even make sense. So over here, suppose we are at this position number 1, and then we start traversing this 1 2 3 4. So we have traversed 1 2 3 4, we have added it to our answer, and then at the same time, the moment we are done with traversing through any node, we are actually going to change its value to something, let's say minus 100, or let's say value number false, or something like that, right? Anything that is not part, that can never be a part of this matrix, and we need to replace our value with this one. So let's say in this case we replace our value with this minus 100, considering that this would not be a part of this matrix. Like, it can be, and then you can change this value, you can discuss it with your interviewer, and then again we start iterating in the same fashion. So again we would have added all the values to our answer list, and again we would have changed all of its values to whatever the value we decided, and we are going to keep repeating the same work up until this point. And notice that at this position number 5, when we try to go upwards, we are going to check that, okay, if the value of this particular cell, if that is not minus 100, then only we can say that, okay, this node has not been visited, and then only we will add it to our answer. But the moment we find out that, okay, this value is actually minus 100, which means we have already visited this node and added to our answer already. So now we have to change our direction in the same manner where we would have changed our direction if we had encountered any boundary, and then we would follow the same path and we would be able to solve this problem. So if we see the time and space complexity, in this case the time complexity is also going to be big O of m cross n, and the space complexity is actually going to be big O of 1 constant time space complexity. Now you would argue that the issue with this approach is that we are actually changing whatever the given input is, and that is not a bad practice, that is not a good practice in when you are actually doing inside the job. But when you are giving any competitive coding interview, your interviewer might expect you to do it. So it's always good to know a better approach. Let's move on to coding now. So first of all, we are going to create an integer called visited, and we are going to assign it some random value. So let's assign 101. Also, we are going to create two variables to keep track of the number of rows and number of columns we have. After that, we are going to have a couple of variables to keep track of the row position and column position we are at, and we are going to initialize it to value number 0. Now we have to iterate over our 4 directions. So we are going to create a 2D array. We are going to name it as directions, and we are going to iterate over all the 4 directions. So we are going to have 4 coordinates that would be used to go to any direction we want to, and we are going to maintain a sequence where the first would be to go to right, then next would be to go to down, then left, and then up. Now we need to keep track of what is the current direction we are at and when we need to change the direction. So we are going to initialize couple of variables called current direction and the change direction, and we are going to assign the value 0 to both of them. So we will have to create an array list to store the result. So we are going to initialize a list of integers to store the answer. Inside our answer, we are going to add the first node of our matrix, which is located at position 0 0. And after that, remember, every time we go through any value, we will have to update that value inside the matrix, because I am showing you the implementation for the second approach I showed in the explanation video. So we will update the value of this matrix node to this visited element that we already set up. Now we will start iterating over our given matrix, and we are going to have few conditions. So first thing is, we need to iterate over the given matrix. Also, we have to iterate over in a particular direction, and the moment we encounter a condition where we are either reaching a boundary or reaching a visited node, we will have to change the direction. So we are going to use current direction, change direction, and make conditions around them. So first of all, we are going to have a while loop, that while the change direction is actually going to be less than 2. And why less than 2? Because we have 4 directions, and at any point we can only go in one direction, and when we are the maximum amount of patterns we have is either we can go on right down or left up path, and that is what we are going to use. Once that is done, we will have another while loop that takes care of all the possible ways where we need to restrict our matrix. First four conditions would be to check that whether we are hitting a boundary, and the last condition is to check that whether we are hitting a visited node or not. If none of this is true, first of all we will have to reset the change direction to 0 because we are not breaking any direction. After that, we are going to update the value of row and column. Then we will add the current matrix row and column position to our answer array list, and then we will update that value for that particular row and column position to visited value. And after first loop ends, we will have to update the values of the current direction and change direction. So for the current direction, we are actually going to add a value, and then we are going to modulate it by 4. We will have to update the value of our change direction. And after both the loop ends, basically our answer array list should have all the elements, and we would have traversed the matrix, so we can simply return that. Let's try to run this code. Okay, seems like our solution is working. Let's submit this code. And our code actually runs 100% faster than all the other solutions, which is pretty nice. Also, I have created a GitHub repository where I'm storing all the problems that I have solved so far, and you can go to any problem and you would be able to find the Java solution for that, and you can use it. It's quite helpful. And I would be posting this link in the solution as well, also this solution in the comments as well, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do set matrix zeros problem, and this problem has been asked by some of my dream companies. So companies are like Microsoft, Amazon, Facebook, Apple, Bloomberg, Adobe, and also sometime in the past there have been Google and Goldman Sachs and eBay. They all have asked this problem, and that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and it is a very well liked problem. Basically we are given an m by n integer matrix, and we are told that at any point if we identify that there exists an element that is 0, then we need to set that entire row and entire column as 0. And we are also told that we need to do it in place. So let's see it with an example. So over here in the example, we are given a matrix like this in the input, and we can see that this is the element that is 0. So because this element is 0, we will have to convert this whole row and this whole column and set it up to zeros, and we need to return an answer like this one. Same goes with this second example, that we are given a matrix like this where we are given 2 zeros at these 2 locations, and because there are 2 zeros, we will convert this entire row and this entire column to 0 because of this particular 0, and we will convert this entire row and again this entire column to 0 because of this particular node. So this row is common, so anyways we will just convert it to zeros, and this would be the final answer we need to return. So suppose this is the example that we are given, and let's see that what could be the most basic intuitive approach that comes to our mind. Well, first thing that comes to our mind is that we can actually start iterating over whatever this given input is, and the moment we encounter a value 0, we can just convert that column and that row where the 0 belongs to and set it up all to all the zeros. And let me show you that why it won't work. So first of all, we'll start iterating over here. We cross this node and this node. We don't find any zeros, so we are good so far. Now at this point, we identify that there exists a 0 over here, which means that for this particular column and this particular row, we will have to convert it to 0. So let's just do that. So if we do that, what we will basically do is we will remove all of these entries, and now we will convert these entries to zeros, which means that this is 0, this is 0, and this will all become 0. Now the problem will happen that after iterating this element, the moment we reach to this particular node, we will again have to convert all of these values to zeros as well. But remember that should not have been done. Why? Because originally the value over here was actually 1, which means that this particular row, this particular column does not need it to be converted to 0 because of this particular node. So that is the problem over here. Let's see that what could be the solution. So let me quickly draw back this to its original form. One thing we can do is we can actually create a copy of this one, and in that particular copy we can actually start making the change whenever we find a 0 in this particular matrix, so that we do not end up changing the elements before they are being visited. So let me quickly create a copy of this particular node. Okay, so now we have created a copy. Again, we'll start iterating over all these elements. We won't do anything over here. We identify that this is a 0 element. The moment we identify that this is a 0 element, we will actually make changes to this particular copied element. So now we will update the elements in this particular fashion. So all of these would be converted to 0. Now again we start iterating over this one. So this is 1, this is 1, so we are good. This is also 1, so we are good. Now this is again a 0. So because this is a 0, we will again update this row and this this column and this row in the copied node. So let me quickly make those updates, and this will be the solution. So in the end we can actually return this copied solution where there is only one entry over here and all the other elements are 0. So this solution would work, but the issue is that we are actually using a big O of m cross n space over here. So let's try to see that can we do some improvement rather than using this additional space. Okay, so in the previous approach we used a new matrix to keep track of all the elements where the rows and columns, the entire things needed to be turned out to 0, but this is actually not necessary. Remember that at any point we identify that inside the given matrix, if there exists a 0, all we need to do is we need to convert that entire column and row, set it up to zeros, which will happen in both of these cases. So because at any point we identify a 0, the change applied to entire matrix for that particular row and column. Why do we use the entire additional matrix to store all the values? This is useless, and better approach is that we can actually create another set where we take care of all the row positions and all the column positions, and all we need to care is that at any point if we identify a 0 at any moment, we simply need to enter that entry in those particular row and column positions and then convert those row and column position to 0. So let me quickly show you how we are going to do this. So over here we will start iterating all the nodes, and we identify that these particular nodes 1, 2 and 3, these nodes, they are not 0, so we are okay with this one, but this is a 0. So because we identify that there exists a 0 node, we will quickly note this position to this row and column entries. So we will add an entry over here called 0, and we will also add an entry over here called 0, right? We are good so far. Now again we will keep iterating over this given input in the similar fashion. So these two are also not 0 and this is also not 0, so we are good so far. Next we are going to do is that because this entry is 0, again we will record those positions inside this additional row and column set that we have created. And now this last entry is also not 0, which means we don't care about anything. And at the end all we need to do is we need to iterate over this additional created sets and see that at whatever position we encounter the 0 value, for that particular row we will convert it to 0, and that particular column we will convert it to 0. So first of all we will visit this hash set of rows, and we identify that okay, first one is 0. So because first one is 0, all of these entries needed to be converted to 0, so we will convert these entries to 0. So we are good so far. Again we identify that second is also 0, so again we will repeat the same thing, and we will get rid of all of these ones and we will convert them to zeros as well. Now this last one is not 1, so we are good, and we will not touch this particular column. Now we will do the same thing for this one. So this is because this is 0, we will convert all of them to 0. So this becomes 0, and this one is also 0, so we will convert all of them, and this last cell also becomes 0. and in the end we can just simply return this newly created matrix. So this is a much bigger improvement than that in the previous one we were actually storing an additional entire matrix where the space complexity is big O of m cross n. So over here the space complexity is actually improved and we are only using big O of m plus n. Why plus n? Because suppose the number of rows are m and number of columns are n, so we are still creating this two additional hash sets with those particular element values. The question is, can we actually do something better and even not using this m plus n space, and can we actually use the space complexity to be big O of 1? And yes, there is a solution that achieves this in big O of 1 as well. So let me quickly show you how. Okay, so previously we were actually using an additional data structure like this one to keep track of all the rows where we need to change the value to zeros. So over here, suppose we identify that there exists a zero over here, we would update that value in this particular place, and later we would know that hey, we need to convert all these values to zeros. And we were also using another data structure to keep track of number of columns that needs to be converted to zero in the same manner. That over here we identify that this is a zero, we will update an entry over here and we will mark this point as zero, and later we would update all of these nodes to zeros. But rather than using this separate nodes, what we can do is we can get rid of them and we can do the same thing by using this first row as an alternative for this original additional data structure, and also we can use this first column as an alternative for that original column data structure. And basically we will do the same concept, but we won't be using any extra space anywhere, and this is a wonderful approach. Now there will be one problem with this one, and the problem would be that over here we would be using this particular row to keep track of all the columns where the value needs to be converted to zero, and same way we will have to use this particular column to keep track of all the nodes where the rows needs to be updated. The problem is that this particular position is actually a point of conflict where there exist two intersecting nodes. So what we will do is, as a solution, we would actually create an additional node and we will use these two nodes. So these three nodes would be working in combination, and for the first column we will need to do is just use this entire first row to keep track of all the columns that needs to be updated. And let me show you that how we are going to do the things. Okay, so first of all we will iterate over this matrix and we identify that okay, this value is 1, so we don't care, this value is also 1, so we don't care. Now this value is 0, so because this value is 0 we will have to make change to this particular row and this particular column, but this is at correct position, this 0 for this row, so we only have to update it over here. So we will add an entry 0 over here, right? Now next thing we will do is we will keep iterating over this matrix. So we'll we'll check these three values and all of them are 1, so we are good. This is also 1, so we are good. Now this value is 0, so because this value is 0 we will have to update over here and also over here, so we will do that. So we will convert this value and convert it to 0. We will also convert this value and change it to 0, and at the end we will just iterate over this element, and this element is already 1, so we don't have to do anything. Now this is the matrix we have. All we will have to do is we'll have to iterate over this and these 6 nodes, and at any position we identify the 0, we will convert that row or that column and change it to zeros. So first of all we will start iterating over this first row, and this is 1, so we are good, but this is 0, so because this is 0 we will have to convert all of these to 0. So let's do that. So this value would be turned to 0 and we are good. Now again we come at this position, this is also 0, so all of these values needs to be converted to 0, so we will flip all of those values to zeros as well. Okay, now we are done iterating over this first row. Now we will iterate over this first column. So for the first column we identify that okay, this particular position is 0, so because this is 0 we will update this entire row as zeros. So let's do that. So we will get rid of this first value and we will change it to 0. Now we will iterate to this next node. So this is 1. So because this is 1, we will not touch this row, so we don't have to do anything. And because this is 0, so because this is 0, we will have to convert this entire row to zeros. But since these two nodes have already been converted to 0, we don't have to do anything, and this would be our final solution. So if we write the answer, we can actually write an answer like this one. This would be our final answer, and we can actually return this as the answer, and this solution works perfectly fine. Let's see the time and space complexity in this case. So the time complexity is actually going to be big O of m cross n. Why? Because we will have to iterate over this entire matrix, and that takes m cross n time. In terms of space complexity, we already know that we are only using this additional node. Apart from that, we are not using any additional space, so the space complexity is actually constant space, and this is the final solution. This solution is very good, and let's see the coding. First of all, we will create an additional variable, and we will create a boolean variable, and we will just name it as first column. We will initialize the value as false, and now we'll have to iterate over the matrix. So we'll need to know the length and height of the matrix. So let's initialize two variables to store the height of row and column of the matrix. Now we'll start iterating over the matrix, and we'll start updating the value inside the first row and first column. So we will check that if inside the given matrix for the first row, if there is any element where the value is actually 0, then we will convert that and we will update the value of the first call variable. Okay, once that is done, we will also have to iterate over all the columns. So we will create another loop inside the loop. And now we simply have to check that whether at any position we are encountering any value that is 0. If there is any value that is 0, we will have to update the corresponding I and jth position inside the first row and column subsequently. So once this loop ends, all the values should have been stored inside the first row and first column. So all we will have to do is iterate over the first row and first column, and we will update the subsequent rows and columns. So we will check that if at any position the corresponding value for the I and jth position, if that is 0 inside the first row, we will have to update the element of the this particular node inside the matrix to 0 as well. And once this loop ends, we would have taken care of all the elements inside the given matrix. But we notice that we are running this loop from I equal to 1 and j equal to 1, which means that we are not taking care of first row and first column. So we will have to take care of first row and first column. Now remember, in order for us to take care of the first row, we will have to check the very first element, which is this this particular element inside the given matrix. So we will do that. So we will check that if matrix at 0 0 position, if that is 0, we will have to update all the values inside the first row. And once that is done, we will also have to check for the first column. So for that, we actually have a variable first column, and if the first column variable, if that is true, then we will have to update the first column to 0. And after this ends, I think we should have taken care of all the nodes. So let's try to run this code. Okay, seems like a compilation error. Okay, seems like our solution is working. Let's try to submit this code. Our submission did not work for this one. Oh, we will have to start from j equal to 1 inside this first column. So let's try to run the code again. Let's try to submit it again. Okay, seems like our solution is working, and it's actually pretty efficient compared to a lot of other solutions. I would be posting this inside the comments, so you can check it out from there. Also, I have created a repository inside the GitHub where I have posted the solution of all the Java problems that we have done so far inside the LeetCode. Okay, so this is the repository. You can go to any problem and you would be able to find the accepted Java solution for that particular problem, and I would be posting this link inside the description as well, so you can check it out.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. So the question we are going to do today is called longest increasing path in a matrix. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Apple, DoorDash, Google, Facebook, TikTok, Nvidia, Amazon, Uber, Microsoft, Snapchat, ByteDance, and bunch of more. So I'm going to pay my utmost attention. I hope you also find this useful. So this is a LeetCode hard problem and also a very well-liked problem, which is a rare combination to find. Basically, we are given an m cross an integer matrix, and we need to return the length of the longest increasing path in this given matrix. Now, how do we build this longest increasing path that we need to return the length of? Essentially, we are told that from every single cell, we can move in 4 directions: left, right, up, or down. And based on that, we need to calculate that what is going to be the longest increasing path. We are also explicitly told that we don't have to care about diagonally moving or values outside the boundary. So let's try to understand this with an example. Suppose in this case, this is the example that we are given. Now our aim is to find the longest increasing path. Now we know that from any single cell, how to define an increasing path. Let's say that we are currently located at this cell number 4. Now we have the option to go in 4 direction: up, down, left, and right. Now from this 4 direction, we only need to go to the direction of the cell that is actually increasing order. So we need to maintain this increasing property. So from this value number 4, what are the places we can go? We can go to 9 and we can go to 8. We cannot go to 6 because this would be a diagonal, and we cannot go anywhere outside the boundary. Now in both the cases, we have the option that the values are currently in the increasing order for this 8 and 9, which means both are legitimate scenario. But our aim is to find the longest increasing path. So from 8, do we have any other option to go to that increases in the path? No. From 9, do we have any other option to go to in any next cell that increases? Again, no. So in this case, from 4, the longest increasing path we can make is going to be 2. But is this the longest inside the given entire matrix? The answer is no. We need to find the cell that has the longest increasing path. So if we take one more example, let's take an example for this value number 1. Again, at this location value number 1, we have the option to go into 4 direction. But let's say that for the ease of convenience, we decide to go into the direction of this 1 to 2. Currently, the increasing path length is 1. Again, from this 2, we have one more neighboring cell that is higher than the value, that is this value number 6. So this time the increasing path value will increase by 1. And again, from the 6, we can go to one more neighbor that increases in the value, and that is value number 1. And originally we started with this value number 1 and we moved one hop. So basically we will add one more over here. So essentially we can create a path that looks like this: 1, 2, 6, and 9. And this would be the longest increasing path in our matrix, and the length of this matrix is going to be value number 4. That is what we need to return in the answer. And the first approach comes to our mind is the brute force approach, the very basic approach that we can take to solve this problem. Now let's try to understand that what would be the brute force approach in this manner. Well, of course, the answer is quite simple. From every single cell, we start iterating in all 4 directions, and from all 4 directions we will see that where we can find the increasing path, and the moment we find the increasing path, we keep on adding the value to our answer variable, and we will keep on adding 1 over here. And same way for our increasing path, we will go to its neighbor, and again we will keep on repeating the same process. So let's try to see the solution I'm proposing in action. Okay, so let's say that for the ease of convenience, we start at value number 1 or this value number 9. Again, from 9, what would be the increasing path we are able to make, and what is the maximum answer we have find so far? These are the 2 variables we are going to keep track of. So 9 does not have any neighbors that are in the increasing order, because 9 is the biggest value amongst all. So in this case, we won't be able to find anything. Let's go to this another 9. Again, same thing will happen. We won't be able to find anything. So these 2 are the values that we took care of.
Now we are at value number 4. Since value number 4 we already calculated that there are only two paths we can take, so currently the increasing path maximum we can make is going to be 2. So answer currently we have found so far is value number 2, that this is the maximum path we are able to make. But let's keep on increasing with next subsequent values. So currently the values we took care of is going to be the first row, so I'm just going to mark them as X, that we already took care of this. Now we are at this value number 6. From 6, what are the options we have? We cannot go here because this is not increasing, this is same. We can go here to 9, so this is good. So from 6 we can again create a path of increasing path of size 2, and then that's it. So again our answer will remain same. We also took care of 6. Same goes for this 6. This 6 we have the option to go to value number 9, and we have the option to go to value number 8, but that won't lead to any further results. So again we cannot move anywhere forward. So we also took care of these 5 variables. Now let's move on to value number 8. Again from this value number 8 we do not actually have any path to go to, so we don't even bother updating any of the variables. Now we are at value number 2, and now things will start to get a little bit interesting. So what are the options for the increasing path we have at value number 2? So first increasing path option is over here, so from 2 to 6, that is good. Again from 6, do we have the option to go for the increasing path? And the answer is yes, that is 6 to 9. So in this case from this value number 2, the maximum increasing path we can achieve is going to be value number 3. So we are going to update our result, and so far the longest increasing path we have found so far is going to be value number 3. So again we are going to update our answer as well. Now we are at value number 1. So what are the options we have so far? Can we go to this? No. Can we go to this 6? Yes. So currently we go to this 6. From this 6, what are the options we have? We can either go to 9 or we can either go to 8. So let's just first go to 8. Okay, now we went to the 8. From 8, can we go anywhere else? No. So in this case, for this particular path, the answer we found is 3. But we still have one more option, that from 6 we can still go to this 9. So even if we go from 6 to 9, we don't have anywhere else to go. So once again the answer is going to be 3 as well. Now after taking care of both of these paths, now let's explore more options, and that option is that from this 1 we can go to this value number 2. Okay, from this 2 we still have option to go to value number 6. From this 6 we still have option to go to value number 9. So in this case we created a path that is 1 to 2 to 6 and then to 9. So in this case we created a path with a path length of 4. That is going to be the maximum path we have found so far. So we are again going to update our values. So this is going to be the current increasing path we found for the cell number 1, and the maximum path we have been able to find is also going to be 4. So we are going to update our answer because we need to enter the longest increasing path, and now we still have one more value that we need to go to. So again from this value number 1 we have the option to go to 1 to 8, and then from 8 we won't be able to go anywhere else. So in this case the maximum path we are able to achieve is going to be 2. After completing or after iterating every single value, we found out that the maximum longest increasing path we can create is going to be value number 4. So our brute force approach gave us the appropriate answer that we were looking for. But was it the most optimal answer? Well, the answer you already know, that of course not. And why? Because there are a few things we can actually make changes to. So first thing we can make change to is going to be regarding that for every single cell we were actually doing a lot of repeated computation, and how we were doing that, let me give you a quick example. So again, let's clean this up a bit. Initially when we were traversing our answer, when we reached to this value number 6, we already knew that from this 6 there is only one path we can go, and that is going to yield us the higher result, and that is from 6 to 9. So the longest increasing path, or the longest path we can make at value number 6, was going to be 2. Now when we came back to this value number 1 originally, from 1 what we did was we went from 1 to 2, from 2 to 6, and 6 to 9, every single place repeating the computation we have already completed, and that is a bad approach. What if we already knew that at value number 6 the longest we can do is going to be 2? Same way this value number 2, the longest we can make is going to be value number 3. So based on this information, if we are at value number 1 and we need to go back to this value number 2, we can clearly see that from 1 we already know that there is an increasing path that leads to 2, but from 2 we already know that the maximum amount of value it can generate in terms of longest increasing path is going to be of value number 3. So rather than doing all of this computation, we could have actually just done from 1 we reach to 2 and see that we already have the computation result for 2. So we could have done 1 plus 3 and the answer would have been immediately available to us as the value 4. So this is one of the major significant improvement we can make. And what this improvement is, this is actually we are storing the results that we have already calculated. So what we are doing is one of my favorite things and one of the most beautiful things that is available in the computer science, that is we are actually using dynamic programming in this case. But on top of using dynamic programming, we are also doing something more interesting, and that is that we are actually rather than treating this as the matrix or 3 by 3 matrix, we can actually treat this as individual nodes, and this individual nodes would have some way of connection with them. How connection? Because we are trying to find a path. Now for this path we are actually given the definition that if only from this current cell, let's say the value of current cell is A, if there is a path from A to B where B is greater than A, then only we can connect A to B and consider it for our path. So rather than treating this as just 2 by 2 matrix or m cross n matrix, we can actually consider every single cell in this matrix is equal to node and the path that we are trying to connect actually as the vertices. And once we do this, after seeing these two words, immediately in your mind it's gonna click that essentially we are treating this as a graph solution, and we are in the graph we are trying to find the longest increasing path. We already know how to build a path, and that is using the greater than or less than relation between any two cells. So essentially we already have a directed graph, and we already know that there won't be any cycles in this graph, because let's say that how does the cycle occur in a single graph? Let's say we go from 3 to 5 up in the same position 3, then we can say that there is a cycle. But in this case it is not possible to have a cycle. Why? Because the relation of this edge is actually based on the property that 3 is less than 5. That's why there is an edge that exists over here. If 3 was not less than 5, then there won't be any edge over here. So which means from 5 to 3 there is an edge, there is an impossible way to create an edge. So essentially this is also going to be an acyclic graph, and we already know that this is a director acyclic graph, and in the DAG or directed acyclic graph we are trying to find the longest path. Basically, rather than treating it as longest increasing path, we are just trying to find the longest path. So essentially now our life becomes much easier. On top of that, we are already going to use the dynamic programming properties. So we are going to know that how we are going to take care of every single value. So we are not going to repeat the computations that we have already created. Now let's see that what would be the solution look like in action. Okay, so now what we are going to do is we are actually going to create a dynamic programming to m cross n grid, and in this case we are going to use this to store that every single element, how many increasing path we can make, maximum amount of increasing path we can make. So this would be a great help for in terms of memorization. On top of that, for every single node, we are treating it as a graph, and we are going to build the graph upon them. So we are not actually creating a separate graph. We can actually use the same matrix. For the visual representation, I'm going to make some circles and some arrows, but you would be able to imagine that what we are actually trying to do. So first, let's say that we are at value number 9. So we are at a graph node like 9. From 9, do we have any edges extending out? No, because this is the same as 9 and this is less than 9. So there is no edges, which means the longest path we can make at value number 9 is going to be of value number 1. Okay, we are good with this result. Now at this second cell 9, again same thing is going to happen, that we are going to have a single cell that is not able to branch out or connect with anything else. So once again the longest path we are going to make is going to be value number 1. Now we are at this value number 4. what are the options we have. So let me just clean this up a bit, and from this value number 4 we actually have couple of options. We can either grow from 4 to 9, or we can go from 4 to 8. So let's say if we decide to go from 4 to 9, do we need to calculate that from 9 how many values we can go to? No. Why? Because we already know this result. So from this 4, let's say if we decide to go to 9, we are actually going to create a path like this, that initially we are going to have a node 4, and from 4 we have the option to go to 9, or from this value number 4 we have the option to go to value number 8. So currently we have two options. From this 8 we don't know how many options we have because we haven't calculated, but we already calculated the result for this value number 9, which means if we decide to go from 4 to 9, we are for sure guaranteed to have an increasing path of 2, because from 9 it does not lead anywhere else. So we are good with this so far, which means and from this 4 to 8, let's say if we decide that from 4 we are going to go to 8, what are the options we have? From 8 we cannot go here or here. So again from 8 there are no possible nodes that we can calculate, which means we are again going to be able to create a maximum path of 2. So in this case, rather than doing all of this computation, we can actually store our answer, and we can just put down the value 2 over here, that this is the longest path 4 can take. Now we are at position number 6. From 6, what are the options here it has? Well, 6, as you can clearly see that 6 is not able to go over here. It is only able to go over here, and this we have already calculated from. So that means that from 6 we only have two options, and that is the longest path we can make is of value number 2. Again from this 6 we have two options. We can go to this value number 8, or we can go to this value number 9. In either case, the maximum path we are going to make is going to be of size 2. Reasons you already know. From this 8 we cannot actually go anywhere else, so the longest path we will be able to make is going to be 1. Now from this value number 2 we actually have just one option that where we can go, and that is to go to this value number 6. But from this 6 we already calculated the results, and that is going to be 2. So in this case we can clearly write the answer as 3. Now from this 1 we actually have multiple options to go to. So this I'm going to draw in the answer, and you would be able to understand what I mean. So initially we are located at this value number 1. From this 1 we have the option to go to value number 6. From this 1 we also have the option to go to value number 2, and from this 6 we have the option to go to value number 8, and we also have the option to go to value number 9. From this 2 we have the option to go to value number 6, and then 6 we have the option to go to value number 9, and currently we are located at this position. So these are the possibilities, or these are the options we can have. Let's assess each path. So in this case, if we go from 1 to 6, then from 6 we can either go to 8, or we can either go to 9. In either case, the answer for this portion is going to be value number 3. But in this case, if we decide from 1 to 2, 2 to 6, and 6 to 9, we are going to get the answer to be of value number 4. So in this case, 4 is the maximum answer we can get, but we don't actually have to do all of this computation. Why? Because we are using dynamic programming. That is the most important concept so far. So from this value number 1, the moment we see that this is where we can go, our mind should click that if we take this path, then what we would do is from here if we take this path, then the sum is going to be 3. But from here, if we take this path, then the sum is going to be 4. So obviously we are trying to find the maximum value, so we are going to store the value 4 rather than storing the value 3, and 4 is here. Now we are again located at this value number 1. From this 1, can we go over here? No. Can we go over here? Yes. So what is the maximum path we can make? We can do one jump like this, and we already know that there is only one single entity path we can choose over here. So maximum value we can get is going to be 2. So this is going to be our dynamic programming graph combination matrix combination solution, and that is why this is treated as a hard problem. But in my opinion, if you already knew these concepts, then it won't be so difficult for you. And after watching this video, I can guarantee that this is definitely not going to be hard for you. So we can clearly see that in the end we only need to return the maximum value that is present inside the dynamic programming graph, and that we can return quite easily, and this is going to be the whole solution. Now this is a very beautiful solution. If we see time and space complexity in this case, essentially the time complexity is going to be big O of 2 times m cross n. So overall we can write the time complexity to be big O of m multiplied by n, which is a very good time complexity. And if we see space complexity, well, this is a little bit more expensive because we are using an additional 2 by 2 or m cross n matrix over here. So this is also going to be big O of m multiplied by n, but this is also reasonably acceptable. This is not very complicated. So in my opinion, this is a very good problem to understand three major concepts, and that is graph, dynamic programming, and also matrix. So everyone should do this problem at least once. Now let's go to the coding part that is not so difficult.
So basically, first of all, we are going to create a 2D array to store all the directions that we are going to traverse over. We are also going to have some private integers that we are going to use. Now, the first idea is to create or to find the longest increasing path. As an input, we are using the matrix that we are given in the input, and we are simply going to iterate over the given matrix. We are also going to create a cache or a dynamic programming m cross n array, and we are simply going to have our answer stored initially as value number 0. Then with using two for loops, we are going to iterate our n cross n array, and we are going to check that whether at any single cell position are we finding the maximum longest increasing path or not. And for to do that, we are actually going to call another helper method called dfx, where in the dfs as an input we are going to provide matrix, the current ith and jth position, so to identify that which cell we are talking about, and the current array that we or the current dynamic programming matrix that we have created and populated. Now inside our dfs method, we are first of all going to check that for any particular value, are we or have we already checked that particular cell value or not, and we are going to initialize the dynamic programming array as 0. So if the value is not equal to 0, then we need to find the value for that, and we are now going to iterate in all four directions from that particular cell. Then we are going to check that we are going out of bounds or not using these four conditions. If not, then we are only selecting the path where the adjacent values are going to be in the increasing order, and if that is the case, then we are going to update the value of our current cache with whatever the maximum value we can find for that existing cache, or recursively calling the dfs method again. And in the end, we are going to add one more value to our cache because we found an additional path that exists. And let's say if we don't find any additional path, still the initial value of cache is going to be 0. So if we increase it by 1, it is going to be added by 1. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code, and our code runs pretty efficiently compared to a lot of other solutions. I would be posting this code in our GitHub repository, and that link for our GitHub repository is actually posted in the description, so you would be able to check it out from there. Thank you.